Recording in progress.
So now we want to just like order logging approximately set covers.
Yeah, so we want to get set cover, but more important, so we'll continue, so welcome to lecture 11. We'll continue our discussion on constructing PCPs. We will want to construct PCPs with, in particular, we want to prove hardness of gap label cover under polynomial time reductions, which have soundness error, which is sub-constant. Parallel repetition gets you soundness error only, which is constant. To get sub-constant, you have to repeat, do parallel repetition a super constant number of times, which means the corresponding reduction runs in super polynomial time. So the question we would like to ask, there are two ways to handle this question. Either we de-randomize parallel repetition, or we try to get an even better PCP from the low degree test itself, and we are going to take this latter approach. So in particular, we are going to prove this following theorem of Raz and Safra. So recap from last time. It's a plane point test. And this theorem is due to Raz Safra. Let's stare at it again. So usually we have been used to line point test. Here, you're given an F. You're given F, which is a truth table on F to the N. And the key difference is going to be, we're going to check S, which is a random plane. We're going to pick a random, so the F has been given to you this way. Forget it. Say you've been given a function, you're given the truth table of a function on F to the M. You pick a random plane and you check if the restriction of the function to the plane is a low degree bivariate polynomial. And you accept if this is the case and you reject otherwise. What Raz Safra are going to show, if this test passes a non-trivial fraction of the time, not 1 minus epsilon fraction of the time like we studied previously, not 90% of the time, but say 1% of the time, then they still want to say there is structure. That is, the function globally does have some non-trivial agreement with the low degree polynomial. In particular, we will prove the following. We'll show that, suppose, in fact, they prove a robust statement. You pick a random plane and you look at the agreement of F with a random degree D polynomial on the plane, a bivariate thing. And suppose this expected agreement is not very small, it's at least an epsilon. And epsilon is something which is larger than what would happen with what a random function would do. So epsilon is going to be something larger than D over F or something. A random function would get like 1 over F or something. This is much, much larger than that. And the expected agreement is more than this. Then what Raz Safra says, then this is, notice this is not like 90% agreement or something. This is like a 1% agreement or something. They say, in spite of this, F then has to have a global structure. F has to be globally has to agree with some low degree polynomial, but not certainly on 90%, but on some other, if not 1%, 0.99%. That's the statement we'll do. That is, if the test, anytime the test passes slightly better than random, actually we would like to, this is open, we would like to show that the moment it passes better than random, it has to have structure. This is a statement we would like to show. We showed this for the BLR test. The BLR, we showed that moment it passes better than half plus epsilon, better than half, that is, it gets half plus epsilon, then it has to have structure. We would like to prove a similar statement. We don't have such a statements in low degree test.
You would like to have 1 over the size of F plus F.
I would like to have 1 over size of F, or to show that there are counterexamples which will have absolutely no structure and yet pass the test. So currently I don't know of either of them. It will be good to either come up with counterexamples which do significantly better than 1 over F. A random example will have 1 over F. I think counterexamples of the size of D over F should be there, but I don't know how to.
D over F is
because of Schwarz-Zippel that comes, but it's unclear. That's D over F comes right now. It comes more because of the analysis. I don't see it coming as a bottleneck to the proof. It's a bottleneck to the analysis. This one. So it will be good if we can. It will be really nice if we can get a structure as clean a statement as we have for the linearity test, and this is open. This is open. What we can do is that there's some sort of non-trivial agreement, then some sort of non-trivial local agreement, then there is global agreement. Okay, and this is the sort of theorem we are going to be proving today. Actually, what we'll see today is 3 things. So the plan for today.
The variant for these 4 lines is looking for.
So the variant for this for lines is known. It's Arora-Suzan. Unfortunately, it's not as clean. There are 2 tables. No, that was Friedel-Suzan. So there is also lines planes which also get it in this regime. So Friedel-Suzan and all were in the low soundness error, in the high soundness error regime. Here we are working in the low soundness error regime. In this regime, Arora-Suzan do have a paper for the lines point. The reason we are not discussing that is its parameters are worse off than this result, and also its analysis is a little more complicated than this. So for both reasons, we are.
What do you test on planes? The query complexity tested is large.
The query complexity on tested. That's the only thing you lose. Yeah, but it's like Q square over Q. The actual size of the proof is Q power M. You are querying Q square things, or Q power M and Q things. So really, it's basically no this one. So at this point of time, the reason one of the reasons why after this nobody cared about the line point test was, but for aesthetic reasons, there was no reason to ask for the lines point test. The planes point test suffices. And you will see there'll be a crucial point which I will highlight, where the planes, there's something you can do with the planes point test which you could not have done with the lines point test. We will see that, and that's the reason why the Arora-Safra analysis is so much cleaner. It's a place where they will be able to argue for planes point and not lines point. And certainly you lose something, you go for planes, you are querying Q square sized objects instead of Q sized object. But when compared to the entire space of size Q power M, these are both essentially the same, this one. Of course, there's this other fact is the amount of randomness you're investing in it. So for a lines point test, the amount of randomness being invested is 2 times log of Q power M, because you have to pick 2 points. For a planes point, you have to pick 3 times log of Q power M, because you have to pick 3 points in space and then pick the randomness one. So this means that any proof that goes via the lines point test possibly is only quadratically larger than the original proof, whereas any proof that goes via the planes point is cubically larger. So that also has this effect. But this is an effect which actually is not such a serious thing, because what we have seen already in the what we noticed in the Friedel-Sudan test, you notice it, we really didn't care to check all lines. It was sufficient if you checked line. If you recall, there was this proof of it had this high dimensional expander sort of, you had this, there was this structure in which, that is, the lines need not have been all lines. The lines need not have been in which X is drawn randomly from F to the M, and H. How do you pick a line? You pick a line by picking 2 points, X and H. X randomly from F to the M, H randomly from F to the M, and that's what causes you 2 log Q to the M. But what you can show is you actually don't need to pick both of them randomly from F to the M. X has to be picked randomly from F to the M. H can be picked from a subspace of F. From H, let F be one space, and H could be, the small h could be from a subspace capital H to the power M. And as long as this subspace is well mixing in this one, it's not too small a subspace, things work out. You can show that the exact same analysis we showed last time works. Therefore, the amount of randomness will be M log Q plus M log H, where H is the size of the subspace. Now, M log H can be made to be epsilon log F. You can make it as small as possible. So even in the lines point test, you could make the proof size to be nearly linear by this argument. And the exact same thing works for the planes point. The 2 extra directions, that you pick a point X and you have to pick 2 directions H1 and H2 to determine the plane. The plane will be Xi plus H1 plus JH2. H1 and H2 could have been picked from a subfield. Therefore, this objection also goes away when you work with the planes point or the lines point test. All that you care for is the cubic versus the quadratic objection goes. Anyhow, they don't get you linear, and there are other means to simplify it. Therefore, so the only reason to prefer the lines point is for aesthetic reasons. Aesthetic reasons, and that's why nobody sort of tried to spend time to improve the lines point test since the Arora-Sudan result, because Ras Safra came and gave a cleaner analysis. But it's worth it for just the challenge that it proposes, and we'll see why the planes point test has an advantage over the the lines point test with respect to analysis. Okay, so what's the plan for today? We'll give a high-level sketch of the Ras Safra analysis. We'll then show how to construct PCPs from this low degree test. We previously showed how to construct PCPs from the Friedel-Sudan test. We then show this. Seems as if it would be done, except that this PCP that we constructed won't have constant sized alphabet. It'll have actually, forget about constant size. You don't expect, if you want sub-constant soundness, you can't expect constant size alphabet. But the alphabet will be super constant, but in fact, the alphabet will be super polynomial over here. So it will be humongously large, the alphabet size that you get from this. So we will have to do a subsequent step called alphabet reduction.
So, constructing PCP from this ability, only test we take a random subset and see if it's close to a regular code.
So notice we have to be limited. So it's going to be more or less just that, except there will be some catches like this is what we did last time, but we incurred several union bounds, which we did when we constructed a PCP from Friedel-Sudan. And those union bounds were fine because all you wanted was to construct a PCP which was 1 versus 99%. But now we need 1 versus epsilon. So you can't afford to incur union bounds all over the place. So you'll have to do the same thing, but But I'll just tell you that if you are careful, these places, you won't incur the union code. So it will be the same proof, but done with far more care and delicacy than before. Okay, so let's go into the saffron. So what we'll actually do in lecture is we'll only prove the case when M is lecture, we'll prove the case when M equals 3. That is planes in a cube. We will not prove anything more than planes in a cube. In this particular case, so the rasa from planes in a cube. We'll show that there exists an epsilon naught, which is Pauli in d over size of f, such that for all f cubed to f, expected agreement of f on a random plane with bivariate polynomials of degree 2 is at least so that's the statement we'll prove. And okay, so this doesn't answer the question because we eventually wanted to go from planes to M, not planes to just cubic thing. Which at the end of the proof, what we'll observe is the same proof.
Yeah, they want a multiplicative factor of epsilon.
Huh?
They want a multiplicative factor.
In the sense?
In the original statement, you say the global agreement is epsilon 0 times epsilon.
No, epsilon minus epsilon 0. Sorry, that was a minus. And actually, it's very important, it's minus. That's a linear term. We'll show that the same proof generalizes to the following. What's the following? It will generalize to not planes in higher dimension, but will generalize to n minus 1 hyperplanes in m dimension.
The screen is closed.
Huh?
The screen is closed.
So what we, okay, the screen, huh? So what we'll show is, so we showed planes and cubes. What we'll show, once you see the full proof, you'll see the exact same proof works for m minus one dimension subspaces in m dimensions. And if that were the case, so more precisely, we're going to change this to m. This will be an m minus one dimensional type.
That will be removed.
Huh?
That will be removed.
Minus one, so that will be b. Two will be m. M minus one. Okay. And why does the final theorem follow from this? Huh?
Agreement of P m minus one, you can lower bound by taking a m minus two hyperplane.
So you'll just inductively do this and it'll just, and then it's because it's linear, it really nicely works out. Otherwise, you'll calculate, you'll accumulate all sorts of multiplicative factors. Here, all that you will get is, you will just get the following, you will just get
External zero will become 10 cent.
m times, or m minus 2 times this. So it very nicely works out. So just then by induction, you will get that agreement of
Should we think of D over F as a constant? Is that mathematical?
D over F, think of D over F as a
So if you
constant.
think of D over F as constant,
Mhm.
then this is okay. So m times epsilon naught is all right as long as m is not. So epsilon naught is a constant.
Yeah, the question is what do you want?
What should we think of m?
So, it depends. So you can think of the m is going to be something eventually in the PCP parameter, something going to be log m or something. Therefore, D over F, typically what I thought to be constant could be thought to be slightly subconstant. But for the very tight applications, actually m will be a constant. M will be 10, 11 or some such thing. Huh? But actually, this is also open. This was open for a long while till paper of Eri Dinur, Amay Bangale and Inbal Livni, where is the, so what do we get out of this? We will get that this is greater than or equal to expected value of agreement F restricted to S, P2D minus M minus 2 epsilon naught, where S is a plane. And it was asked, is this M necessary over here? Can you get rid of this M? And today we know how to get rid of this. So it works even if just D over F is a constant. But unfortunately, it's not the plane point test. They go to a cube point test and they show the cube point test does this.
And this is true in the Ras-Safra regime, where the acceptance probability.
Yeah, it's true in the, so right now, look, all these statements I'm talking about in the, everything I'm going to say is in the Ras-Safra regime, Ras-Safra Aurora Sudan regime. So the question is, does an M required? M is also not required. This is subsequent improvements have shown that.
But that's for a different test.
That's for the cube point test. So we believe all of these improvements can be got even for the line point test. That is, each time you want an improvement, they are going for a slightly different test. These tests don't matter much with respect to constructing PCPs, like whether you can do a line point test or a plane point test or a cube point test, really doesn't matter. But aesthetically, I would like to get all of this for the line point test, which we don't yet have. So in some sense, other than for aesthetic reasons, we have all the answers we want, but I think it's worthwhile pursuing things for aesthetic reasons. Huh? Okay, so what was all the spiel about? The spiel about was stating it's sufficient to work with planes in a cube, and we'll forget about everything else. Let's go to planes in a cube. And this proof is actually, it's quite remarkable. Rastafari, they're going to use, it's a very, very non-algebraic proof. They'll use algebra in a very one. So you're given the plane points table. From the points table, f cubed to f, let's construct the planes table. Which is for each plane, let's find the best fit plane that is for each plane S, it's the best fit plane, and you break twice best fit polynomial. Best fit polynomial for that plane. And you break ties arbitrarily. If there are more than, notice we are we are way past the unique decoding regime. Therefore, there might be multiple planes, multiple polynomials that have the same agreement with this. And we'll just pick one of them at arbitrarily. Break ties arbitrarily. Okay. What I want to ask is the following question. Now, let's pick a random line and two planes S1 and S prime that contain this line. And let's ask what's the probability that f of S1, f of S restricted to L is not identically. So, okay, let's first assume, let's start off with delta being the probability that when you pick a random S and a random X, f of X is not equal to fs of X. This is essentially the plane point. This is the hypothesis for the expected agreement with the plane. So let's, delta is our number, which we have called epsilon or something earlier. Let's fix delta to be this. Now, given this delta, I want to ask the following. What is this number?
So delta is just essentially so after you pick S, you're just looking at its distance. This best fit you want to.
It's the distance to the best fit. The distance to the best fit, which is also exactly, it's exactly this quantity. It's exactly this as expected. What I want to ask is, let's ask this. So let's pick two planes completely at random, S and S prime. Now, these two planes, because they come from a cube, there can only be two possibilities that can happen to it. Either they are parallel or they intersect on a line. If it was 4 dimensions, these planes could be skewed. They could not intersect at all. And this is where we are going to use planes in a cube. You pick two random planes, they are either going to intersect in a line or they are going to be parallel. The probability that they are parallel is very small, it's just 1 over q. That is, given you picked one plane, the probability that you pick the other plane also to be exactly this one is very little. Therefore, we can the 1 over q, the losses like 1 over q will keep accumulating all over the place. So with high probability, these two planes that you pick up are planes that intersect on a line. So what I'm going to ask is, I pick two random planes S and S prime. What is the probability that Fs intersection, Fs when restricted to the intersection and Fs prime when restricted to the intersection are not equal. So let's define this. I want to understand this. So let's define this quantity to be, say, epsilon. Okay. I want to ask how small can epsilon be?
This is like a collision possibility.
It's almost collision probability. So collision probability is what Ronald is referring to is the following thing. Suppose I did the following experiment instead. Pick X and pick two planes that contain X.
Is it a line?
Huh?
Here,
X is a point. X is a point. X will be a point, L will be a line, S will be a plane. This one. And I ask f of s restricted to x equals, if not equal to f of x. Sorry, this is not what. Sorry, I think I flipped everything here. This is equality here in the other region. Delta is this. And the same thing is true over here. I'm asking about equality. So let's ask this property.
is screen.
No, screen is fucking fine, no?
Okay. Yeah.
Let's ask what is this? This is exactly something like, it's a little more than collision probability. This is exactly, this in fact is expected value over X, probability that I pick an S that contains X. F of X equals f of X. Sorry, and the square of this. That's exactly this quantity, which. Okay, am I right about this? Yeah, I'm right about this. So this is certainly greater than or equal to expected value of X. Probability S in X. The whole square. This is just Cauchy-Schwarz. But notice the one below is exactly the original delta that we started off with. So this is delta square. Okay. So you pick a random S and S prime and you pick a random point on it. The probability that they all agree is at least delta square is what we have. Whereas the quantity which I care is what's the probability that they agree completely on the line. Now this is a Schwarz-Zippel. That is, suppose they don't agree on this line. Then the probability that you happen to pick a point on this line where they disagree is exactly d over s. Therefore, you can show that this quantity, hence this argument will say that hence probability I pick S and S prime such that f of s restricted to S intersection S prime not equal to f of S prime S intersection S prime, sorry, equal to is certainly at least delta square minus d by q minus 1 by q. The d by q comes, 1 by q comes because it could have happened that the S and S prime were actually parallel planes, in which case I completely give up. I lose the 1 over q. But for 1 over q, they are not parallel planes. Now, if they were not parallel planes, they intersected on a line. They could have been that on that line, they actually are two different polynomials. But then you are unlucky and happen to pick a point at which they agree. That happens only with probability d over q. You put all of them together, this is what you will get. So we end up with this conclusion. This is great. So what do we have about this? We have that the plane, you have this planes point, the planes, you have a function on the planes, and they are mostly in agreement with each other. Just take two random planes, they're random planes in this cube. They agree with each other with probability delta square minus b over q minus 1 over q.
So I understood the argument about.
Mm-hmm.
So now you're picking two planes.
So suppose this was less than this, then what would happen? One error could have been the fact that you actually the planes were parallel. So you add another error 1 over q. The other error could have been the fact that you picked a point in which they disagreed, but they happen to agree. That could be d over q. But for that, they should be completely, this experiment should have satisfied, and that you already showed is delta square. I'm not writing this word, but that's basically what's going on there. Yeah. Okay. What is this? Actually, that's all. All the algebra we've thrown out of the picture. We're going to have what's going to have. So we're going to look at this graph. What's the graph? We're going to construct a graph G, whose vertices are the set of all planes, and edges are between planes that are parallel, these are very small, or consistent with each other.
Consistent with each other means? Consistent with each other.
What that exactly is my definition of consistency. That is two planes such that so every plane has an associated polynomial with it. We'll say two planes are consistent if on the intersection, firstly, if they are consistent, if they don't have an intersection, or rather, they are consistent if on their intersection they happen to give the same value. If the intersection is empty, so be it. Then they give the same value. That is consistent. Where consistent is.
If parallel planes are automatically consistent.
Yeah. So consistent is if two planes agree on their intersection. Okay. So we are looking at this graph where there are these edges. And what does the thing in gray tell us? That the number of edges, there are potentially mod v square edges in this. Could be mod v square edges. Out of them, actually a delta square fraction of them are edges. It's not a sparse graph by any means. It has a lot of edges out there. Okay, so this graph is an extremely dense graph.
So the density is essentially that number.
It is exactly that number. It's delta v square. We choose 2 or some such thing, but modulo all of the delta square. So this is the graph which we have. But suppose the graph came from a polynomial. Suppose the graph actually came from restrictions of a global polynomial, how would it look like? Which agreed with the function on epsilon. So suppose epsilon fraction of the planes actually agreed with a global polynomial. Then you would have a clique of size epsilon, and that would be this one. And I don't care how it is. There will be one large clique in this graph. If the graph was what we want to, if you want to what we want to show, then if you finally our conclusion demands that we want to show that there's a large clique in this graph. And from that clique, we will want to extract the global polynomial. Well, let's ask what is it that prevents this graph from having a large clique? And a clique is not a very large. I don't want a clique of size mod v over 2. I want a clique of size which involves epsilon mod v edges. Epsilon mod v of the planes. So then all those guys I will interpolate together to get one global polynomial. So let's just ask what can you have such a dense graph without having any clique in it? Notice this. You can do Turan's theorem, but there are things which actually will go much simpler than it. There are things that is you can have extremely dense graphs without having a clique in it.
Low degree.
For example, what prevents you from having a clique? What do we want to prove? Let's want to prove large clique. Actually, we'll use algebra once more in this graph. So let's ask what prevents. I'll have to stop at 11 o'clock. Let's see what prevents cliques. In prevent, what's a clique? A clique is a completely transitive graph. That is, if I have an edge from A to B, B to C, I must have an edge from A to C. Clique should have this property. So let's ask. So suppose there was a non-edge between two planes. S and S prime. There was a non-edge. In other words, S and S prime are inconsistent. They are not even parallel. They are actually inconsistent. These are two intersecting planes, and on the intersecting line, they actually give a different value. What I want to know is, let's call it S1 and S2. What are the structures that are going to prevent us? Structures like these that are going to make the graph a non, which is not going to have a clique. If there were an edge, if there were a vertex S that is connected both to S1 and to S2, that's what's going to cause issues. So whenever you have this sort of a wedge in the graph, that is a non-edge, a triangle like this is what's preventing you from. If there were no such objects in the graph, then I claim the graph is only formed of cliques. So let's look at it. So let's ask. Let's make this is actually the crucial rasa for our claim. Suppose S prime, sorry, S1, S2 is not an edge in this consistency graph. Then let's ask, okay, so this is a non-edge. So these two can't be part of the same clique, or at least that's what the graph is telling you. How many S's can be there? What is the probability over S's such that there exists? What's the probability of X? That either yes, S1 belongs to the edge, or SS2 belongs to the edge. Sorry, and, sorry. No, this is not even delta. Even So notice that S and S1 and S2 are two disagreeing planes. That means there is a line that observes its violation. Now in order to be an edge should be parallel to one of them. So once again, this will be a 1 over q probability I'm going to give up. So S should also be something that intersects this line. If it happens to intersect this line on one of the, it can only have an edge between them if it happens to intersect it on the agreeing points on this line, which is only d over q. All the other points, it can only agree them with one of the two, this ones. So I'm sure Zipple is once again coming. So all I want to claim is this is at most d plus 1 over q. That 1 over q is for taking into account parallel. The d over q is you pick a random other plane. It's essentially going to pick a random point on this line. And that point, had it been a point of disagreement between S1 and S2, they can't have an edge. You're only unlucky if you happen to pick a point which happens to be an agreement point. So whenever there is a non-edge, the fraction of S's for which such a thing happens is really, really small.
You really mean 2 over, it could be parallel to either one. 3 over 2, this 2 over 2 is.
So strictly speaking, all I want is there is this line. If S is parallel to this line, I can't do anything for it. If S intersects the line, then I begin. So 1. So the question is, so you have a line. So because it's a non-edge, there is a line. And now you're going to look at whether S is going to be parallel to the line or S intersects the line. Yeah. So S is parallel to the line with probability 1 over q. That's this one. Otherwise, it's d over q. I'm not writing the proof, but that's basically what it is. And that's actually, this is the one, I would say, the heart of rasa for us. The crucial observation they do that this is a graph in which every non-edge actually has very few such wedges out there. So this suggests a very natural thing. Just throw out these wedges out of the picture, and hopefully once you throw them out, there are not too many such wedges. The graph will break up into union of
So you're going to throw the vertex S out.
So what we will do is we will sort of do the following pruning process. One, we'll do the following. So let's call epsilon to be this d plus 1 over q. So if there exists a vertex that has too small a degree, so this vertex is too small a degree. So even if it were part of a clique, it's going to be a part of a clique of size 2 root epsilon. So what I'll just do is I'll just throw out all the edges going out of this vertex. I'm just going to do that. If there is a vertex, I'll do this. Yeah, I'm going to just keep doing this as long as I keep doing it. I pick R in an arbitrary order. Otherwise, remove all edges between. So you have a vertex now. This is its neighborhood. And we know n of v is larger than or equal to 2 square root epsilon times mod v. And let's call this n2 of v. These are things which are reachable from this, but not reachable. That is, things which are step 2 from this one. Then remove all edges between n of v and n2 of v.
It means for a single lever.
So if there is, so take an arbitrary vertex. If it is of if it is of low degree, just remove all the edges between it and its neighbor. If it is of large degree, remove all the edges between its neighbors and its next order neighbors. And do this for every vertex till you cannot do this anymore.
But the second case I can.
No, you cannot always do it. It might be that there is no second order neighbors. So when you can stop this process, the graph will be a union of cliques. So what's the process? The process is take every vertex. If it is a low degree vertex, remove all the edges between it and its neighbors. If it's a large degree vertex, remove all neighbors between its neighbors and its next order neighbors. There might not exist any such thing. If this graph, if V was part of, if everything that V was connected to was a clique, then there are no such edges over here. So you keep doing this process. Notice that when you stop this process, the graph will be a union of cliques.
We have to argue that there are large ones. Yes.
What I want to argue, firstly, by what we'll argue is by doing this process, we would not have thrown away too many edges. The graph still has a lot of edges left. And for that, this lemma will come to our rescue.
So it's basically talking about planes that we needed first, any two to be intersected line.
Yeah, any two planes agree intersect on a line.
There is not true that any 2 points intersect on a line.
So that's not true for the line point test. So two lines intersect on a point, and you really can't say, if two lines intersect, you can't say anything about a third line being consistent with both those. And this is exactly where Ras-Safra have to get their advantage over this one. That is, they are able, the fact that these two lines are disagreeing, locally they are able to capture something out of it. Whereas the line pointers, locally we won't be able to capture anything out of it. It's only when you assimilate a lot of global information, this inconsistency will be, you'll be able to see the effect of this inconsistency. The fact that the intersection between two planes is a code. This is a very important property that Ras-Safra used. And that's the heart of this lemma, which is not feasible in the line point test. Okay. I'm going to sort of hand away from now onward. This lemma, from this lemma, it's going to be very easy to prove that the number of edges you drop out is very small. Because this lemma basically says, when are you going to drop an edge? For every edge that is dropped, for every edge that is dropped.
But when you remove I, it's don't more edges for. In the first case, when you remove all the edges from low degree vertex,
Yeah.
you get more of these structures.
When you remove an edge, once again, claiming. No. So the point will be the moment you remove an edge, those two things go into two different components. Look at the way this.
Okay, this B gets isolated.
They get isolated. They are just making. So you are only the graph is only going to get broken into smaller and smaller components. Therefore, that your problem will not arise. And you can for want of time, what is it? From this lemma, it's going to be very easy to prove that this pruning process will not throw away too many edges. So at the end of this thing, we will still have a very dense graph, which will be a union of cliques. And that's basically the entire rasa of our argument. It's a union of cliques. Take a clique which is, there has to be one clique which is large. If all the cliques are very small, there can't be enough edges in the graph. There will be one clique which is at least of epsilon mod v. Take that clique and just interpolate from that to get a polynomial, and that will satisfy all the requirements. That's going to be their whole proof. You'll have to, there's lots more work to do. There's one technical issue because we have gone from delta to delta square, which is going to cause a problem because we wanted things to be linear in epsilon. If you remember the proof, this is what I wanted to prove. That is the loss is this one, but already I have gone to delta square by going to the plane thing from the plane point. So what we'll be able to prove is we'll show delta square minus epsilon naught. This is not good enough for us because for doing this extension, we needed it to be linear. Notice, by the way, nothing in this proof involved planes in m dimension, 3 dimensions. It could have worked with m minus 1 dimensions in m dimensions.
The cardinality would have been
Which cardinality?
images
Of?
even into vertices that are not connected. What is the number of common neighbors? That
It will be the same d, everything will be d over q. It's all of them will be Schwarzschild. All of them will be Schwarzschild. So all the lemmas I stated will be exactly as they are. And that's basically the entire rasa for a proof. So it's a very clean proof. It uses algebra only in two places. One is going from the plane point test to the plane test, that is that d over q loss. And then in this.
So how do you do interpolation? So now you have a set of planes that are consistent with each other.
You have a subset, you have an epsilon subset of planes which are pairwise completely consistent with each other. Now what
at any point of intersection, you know what to write.
So how it will go? We will show because the subset is at least epsilon or density, there will exist at least two parallel directions, two distinct directions, such that you have d parallel lines in one direction and d parallel lines in another direction. It can't be that every direction sees only less than d minus 1, guys. There will be at least two directions in which you will see d.
These lines are the lines.
No, you have planes now. You have a bunch of planes. You have planes. You have a large fraction of planes. You have epsilon fraction of planes such that they are all pairwise consistent. Fair enough. Now you need to globally interpolate. Now I want to show, because you are epsilon fraction of lines, there has to be at least two directions in which we see at least d minus 1 parallel planes. Because otherwise it would mean that in every direction you only see d minus 1 over f planes, and the number of planes then totally will be too small. Therefore, there will be at least two directions in which you see at least d over f, this one. So now take one of these directions, d over f. So you take d over f. Once you have d over f parallel lines, you can now interpolate a degree d polynomial in every direction except this one direction which is left out by the parallel planes. You can get a degree 2d polynomial. You have d parallel planes, each of which you have a degree d polynomial now. Therefore, now you can come up with an extra variable over here, which will be a degree d over there and a degree. So you have a global polynomial of degree 2d that is completely consistent with this one. But this degree 2d polynomial should be consistent with this other degree d parallel, this one everywhere. Therefore, actually that will collapse to a degree d.
So this is like the row column thing happening here.
There will be the row column thing happening here. So there is a sort of a tensor thing happening here. So it will collapse to a degree d object. And hence you will show that there is one global guy, and then you have to show that this global guy actually has to be consistent with every guy, but all of that is fine. So once again, there'll be Schwarzschild. It's basically, you'll have to fight against things being larger than D. Epsilon has to be significantly larger than D over Q. But that's the whole. So you have a large enough fraction of planes that are pairwise consistent, you can from, but this is true of lines also. If you have a large fraction of lines which are pairwise consistent, you can interpolate a global polynomial. So all of that, everything works for lines also. The only thing that does not work for lines is this lemma, where we are using that the intersection of two planes is a line, which is the chord. This is not true for lines. The intersection of two lines is a point, which is not a chord. I'm going to stop the, I'm not going to proceed Rasa-Safra. The rest of it are details which can be done, but this is the main high level idea. And it's actually, the proof is, this is extreme. Compared to other proofs, which are very algebraic, whatever is a beautiful proof of the loading data. It's an amazingly clean proof.
So the combinatorial that we needed was that if the number of such wedges is true, then there is a large group.
There's a large group. Basically, this Crony product. The combinatorial is just this. So all of these details are in this one explicitly spelled out in the notes from 2010. You can complete this proof and get the statement we want. There is a lot of more technical details because it's what you get is delta and not what you get is delta square and not delta. So you have to do some more hard work to finish all of this. Everything can be done and you can get this proof. Finally, you'll get the Rasa-Safra statement. And product is. Tweaks. One tweak should be large. Interpolate. Large tweak. Obtain a global. I would recommend you read the notes from 2010. So these are notes written by Newton. In fact, that's possibly the best exposition for the Rasa-Safra. The Rasa-Safra paper itself doesn't have such a clean exposition. I think Newton did an amazing job when describing the notes from that time. So she added far more. Even then I hand waved a lot, but Newton filled in all the details and the proof is complete. So I need to go for a meeting now. I'll take a 10-minute break. So let's meet at 11:30.
That is 25.
Huh?
That is 25.
No, the meeting is.
Recording progress.
Okay. Welcome back to part 2. So we put together everything that we have done so far. This is the following statement which we would have. We will be able to prove the following statement of Rasa-Safra. There exists an epsilon naught, which is m times poly in d over f, such that for all functions f, fm to f, the agreement, let's write it this way, if the local agreement is large, the local agreement of bivariate degree D plane is non-trivial, then globally also it agrees to an m variate degree D polynomial But for this. We more or less proved this modulo some caveats. And you need to look up the notes for these things, but the main ideas at least that go into this are all over there. Equivalent formulation of the statement. The following list decoding statement, and this will be very useful for us. And what do I mean by list decoding statement? Notice that when I say that there is a polynomial agrees, it might be the case that there's not just one polynomial that agrees. There might be multiple polynomials that actually explains this data. That is, right now I'm saying if there is non-trivial local agreement, there is non-trivial global agreement. This global agreement need not be from one polynomial. There could be multiple. It's not, we are well past the unique decoding radius, that there could be multiple global polynomials which have the agreement epsilon minus epsilon naught with the given guy.
This is beyond the Johnson radius.
No, it won't be beyond the Johnson radius. So all the epsilon naughts will be larger than square root d over q, which is the Johnson radius. Therefore, these will all be within smaller than the Johnson radius. Therefore, they will all be within the list decoding bound. They will all be within. They won't be more than 1 over epsilon fraction of such polynomials if they are, but they could be more than one polynomial. So, in particular, I would like a statement which gives explanation for all the polynomials together. So, one way to get it is take this one. So, suppose we manage to get one. You manage to get one agreement polynomial. Now you can go back to the given polynomial wherever. So suppose you manage to show that f agrees with one polynomial q1, epsilon minus epsilon naught fraction of the time. Let's go to f, wherever f agrees with q minus q naught, let's put a bot symbol. And now ask, does this new points table still pass the low degree test? It might still pass the low degree test. If it passes, then there exists another polynomial. Pull out that polynomial cannot be q because you took away all the points of agreement with q. So you'll get another polynomial q2. Once again, go and put all the things with bot in it, run it. You'll get yet another polynomial q3. Keep doing this till you'll exhaust it with 1 over epsilon fraction, because each time you are 1 over 1 epsilon fraction of the points, you are botting them out. Therefore, you could potentially expect that there are not just one polynomial that explains it, a 1 over epsilon fraction that explains the whole data. And in fact, we can show the following statement. We can show that for all, we can show the statement. There exists a delta naught. This delta naught is related to that epsilon naught, but not the same. And this is certainly larger than the Johnson radius, such that for all delta greater than delta naught, given any function f to the m to f, given any such function, there exists q1, q2, ql polynomials in PMD where L is order 1 over delta. There exists at most, that is, F success can be fully explained by these L polynomials, such that the following happens. Probability that if I pick a random XS pair, point and a line pair, f of x, so that for all f on planes P2D, f of x equals fsx. That is the planes point test passes and there does not exist an I in L such that Qi restricted to L does not explain Qi restricted to not L, Qi restricted to S. So let's stare at the statement for a while. So what's the statement states? States that the probability that the points plane test passes, but it's not explained by one of these global polynomials, is really tiny. Whenever the test passes, but for this delta fraction, it has to be because of one of these global polynomials. Otherwise, the test cannot be passed.
How much do you care about the L being order 1 over delta? What if it was a very large function delta?
Poly 1 over delta, we will see this in the next immediately when you apply it to. So the way it's going to get, so why is this will be the more useful statement we will work out, and this statement is the proof of this is going, I'll not do the proof of it, but the proof of it is essentially what I just now said. You will just peel off polynomial after polynomial and get this.
So this delta zero is the same as the epsilon zero.
It's related to it, it's not the same. Notice out here, I'm not even stating that the f passes the low degree test reasonably well. I say if it passes the low degree test, it's explained by the exponent. It might be that it just fails the low degree test miserably, in which case I don't care. That is, whenever it does pass, its passage is because of these global polynomials. Okay. So questions on this statement. Let's actually it's the same statement as above. It can be shown, this statement and the previous statement can be shown to be equivalent. You can go back and forth between them. There will be a loss in epsilon naught and delta naught as you keep going back and forth. But these happen to be equivalent statements. One direction is basically what I just said. The other direction requires more care. But you can prove that too. And both of these are, by the way, there in the notes. All of this is there in the notes. So, and the second form is what will be useful to us. So let's stare at it for a while and let me know if you have any questions on this statement. By the way, notice the Rasa proof essentially did give us such a statement. It told us if we didn't care about the line point test, but if we cared about the line test, the plane test, it basically said, but for the planes, but for this fraction of things which we threw out in the pruning process, the graph was broken up into a union of peaks. Then you threw off the small peaks, which is another small fraction. So, but for those two, so there are two things where you throw out. One, you throw off edges, which you did in the pruning process. And the next you throw off things which are from small cliques. We essentially say every large clique corresponds to a global polynomial. They can't be more than 1 over.
Each large clique gives rise to a QI.
Huh?
Each large
Clique will give rise to a QI. And essentially we are saying that if the plane test passes, the probability that the plane test passes and it's not part of the large clique is extremely small. That's exactly the statement we proved. Because when does that happen? That happens only for the edges that we are throwing away. And there are very few such edges we threw away. The edges which happened in the pruning process and the edges which happen to come from small cliques. So this is essentially what the Rasa thing gave. It didn't give it for the plane point test. It gave it for the plane test. And there's some work to go from the plane to the plane point. But it did actually just, the Rasa analysis essentially just popped out this statement. Okay. Okay, now what we want to do is now do our step 2 of the plan today. Construct a PCP from this low degree test. Okay. Recall, how did we come? So let's go back to our PCP from the Friedel-Sudan low degree test. How did we construct it? First, we constructed a PCP. First, we constructed something for the 0 and sub Q, and then we talked about arithmetizing the whole SAT and stuff. So let's start off with the more basic thing, just the 0 and sub Q. So what I want to ask is f close to a low degree polynomial, which is 0 on a particular sub Q. So the more simpler question. Is f can close to a low degree polynomial Q such that Q restricted to say some h to the m is identically 0. How did we do this then?
Your certificates from combinatorial tools and stuff, and
So we said the proof for this would be basically to show that Q was low degree. The Q was low degree if we wrote it as GH xi Qi of x, where GH of z is just product of z minus h in h. The claim was Q restricted to h to the m.
is GHI of X.
Q is identically 0 if and only if there exists Q1, Q2, Qm. What's that? What?
What is Z minus HI there?
Z minus h, no?
If you take the I,
Yeah, but there I put GH of xi. So each one it. So,
but the H's should vary over the I point.
huh?
Yeah, in the product, Z minus H, not the H vary over the I coordinates of H.
H, so it's h to the m. So I'm not taking h1, h cross, h2, hm. It's always, I'm always working on h to the m.
Oh.
Yeah, so that's why. Otherwise, it will be a different GH for each of them. This was what we did last time. So this was the statement which we had. We would like to do the same thing. I would like to do exactly the same thing. I would like to show f is not just low degree, using low degree test, but f is actually close to a low degree. And you can do exactly the same thing now. Instead of giving me f, give me this bunch of polynomials. You give me this whole table of polynomials, q1, q2, qm, and we bundle them all together like we did in the past. That is, when I query a particular point x, I get q1x, q2x, q2. Rather, I don't get q1x, q2x, because I get the purported values for q1, q2. The prover might have cheated. So,
we had a code on top of that to make it a robust.
for robust PCP, we will not. Let's work with the field f now. To get into the binary, the alphabet, we had to apply a error correcting code. For now, let's just this one. So now all I want to know is there were union bounds that were happening in play, and I want to now show you can do this without the union bound. So now what will be the proof? The proof now? The proof now will be a single Q bar going from F to the M to F to the M. Where each Q bar of x1, x2, xn, I view it as Q1 of x, Q2 of x, Qm of x, where each Qi is actually supposedly supposed to be the Qi in the honest. And what will be the 0 and subcube test? Zero and subcube test will be the following. We are given this, that's the object given to me. That's the proof. The test. Pick a random plane, yes. Query Q prime on S. Check that each restriction Q bar I restricted to S is low degree. Check each one of them is low degree. In fact, if any one of them is non-low degree, just reject. 4. Okay, there's also F plus M, so I accept if Q0 at X equals summation GH Xi of Qi at X.
Recording in progress.
Just check this. That's what we did then, and I'm going to claim we'll do exactly the same thing right now.
So, during the PCB composition, we had the problem about using union bound for the outer PCB.
Yeah.
Is the same problem that we are going to work on. In there, you just handle and say, you don't actually need to get anything.
No. The composition will come later on. We are even before composition.
Yeah, no, I think during the previous videos you can LED this,
Yeah.
you are using an outer PCB for it.
Yeah.
We are saying that some errors should accumulate because of the union bound, because we are checking M minus one low degree test.
Yes.
Then you somehow said the union bound error actually will not matter if you bundle then.
Yeah. So we are doing the same bundling over here also.
It's the same phenomenon, same thing is going to happen.
The same, yeah. So we have already, so the bundling happened there. We're going to bundle here also. The bundle here also. What's the and the 0 and subcube? How did I analyze it then? I said. So then
You said if you read the book, somehow the union bound error will not come. So,
yeah, so exactly the same union error bound does not come here too. Union error bound does not come here, but there will be one union error bound comes that we can accommodate, and that will be the question related to Ronald's question: how large can L be? So now let's look at this. Let's look at this object over here. So I want to ask, what's the probability that this F is actually far from a low degree test? F is actually far from any function that is close to a low degree polynomial that is 0 on the h to the m. Now notice that given the function f, the low degree test commits us to polynomials q1 to ql. It says there are such fixed polynomials q1 to ql. There's no the low degree test analysis says there's no option. There are these things, and with very high probability you will always see either the low degree test will fail, or you will see something that the what you see on the behavior of the polynomials q1 to ql. But each of the polynomials, now these are honest to God polynomials. If they are honest to God polynomials, we are only going to incur Schwarzschild error. And there are L of them that are going to incur Schwarzschild error. So all I want to claim is at the end of this, I'm going to have that for without proof, I'm going to prove this. That is for all functions f bar, or rather q bar, from f to the m to f plus 1. There exists q1, q2, ql, and their corresponding actually.
So these are the QIs that you're constructing. These are based on the fact that Q bar I sub S is
The q bar is, you just look at the first component of q.
So it's the low degree test for that gives you a list.
That gives you the list.
One of them gives you
The list gives you a list. Among this list, some of them are actually things which are 0 on h to the m. Keep them, prune the rest. Throw away the remaining guys. So q1, q2, ql are the ones which are honest to God things. List of each q1 is a list. So how am I getting q1 to ql? Q bar is n plus 1 functions. The first one of which is the low degree test in which you applied. That gives you a list. Take that q1, q2, ql. That those polynomials could be 0 on the subcube h to the m or not. Take only that sublist which is 0 on the subcube. So that is, and then for them construct the remaining q1 to qm, and these are the polynomials q1 to ql. Let's say. What I want to claim is the exists q1 to ql, also f to the m plus 1. These are all honest proofs. Honest low degree proofs, such that the probability that when I pick a random plane, q bar passes the 0 on subcube test, and that exists an I in L such that q bar restricted to S is not identically equal to qy restricted to S, is less than or equal to delta plus L times d over q. I'm going to incur a Schwarzschild error for each of the elements in the list.
So, there is one question. So, why can't it be the case that each q agrees with a different qy? So consider the j coordinate of q bar. Suppose it agrees with the kth polynomial.
No. So once again, let's see how am I getting q bar. What is q bar? Q bar, the first coordinate, the q0th coordinate is the original function f that we are going to check. q1 to qm, the remaining m coordinates are the ones which are given as proof for the subcube, this one. So just the q0 part, the low degree. So the low degree test analysis is going to tell you just for the q0 part, if you forget about everything else, it's going to commit to you to L polynomials in the low degree test. Take those L polynomials. Some of those L polynomials might be 0 on h plus m, some of them might not be. The ones which are not, throw them away. The ones which are the ones which I am retaining, which I am going to call q1 to ql, and the q1 to ql bar are for those polynomials. I am going to extend it with the natural extent. So those are what I am calling q1 to ql bar now. Okay.
But how do you know at least one of them vanishes from each power?
None of them might vanish, but in that case, I will catch all, the test will pass all, the test will fail all of the time, because if none of them, so you know that if the test passes with very high probability, it will actually, one of them will actually, the test will actually see the behavior of Qi on this locally. But if Qi is not zero on the h to the m, because of Schwarzschild, you will observe that Qi will, and that's why the extra LD over Q is going to come.
Why is it 1 over? So how big is your subgroup?
Huh?
Should be D over size of H? Or
Which one?
the error there, the Schwarzschild error should be D over size of H.
D over Q, no?
I thought I understood. Can I say this?
Okay.
So you have this, so your proof is going to give you Q naught and the Qis.
Yes.
Now we know that the low degree test passes on these things, otherwise step 3 you will reject.
Yes.
So you got so for each coordinate you get a list,
Mm-hmm.
and now you want to understand, so now I want to check the next identity.
Yes.
So, okay.
And your Schwarzschild error is from the next identity.
The Schwarzschild error is from the identity which I have put here, yes.
Okay, that should be D over Q. Why is there an L there?
Because it could be, I do not know which, it could have been any one of these guys. There's a union bond going across all of these lists. That is, I could have chosen a plane that this plane could have been good for this polynomial, this plane could have been good for this polynomial, this plane. I'm fighting against L different identities. None of these L polynomials should have vanished over here. There are L polynomials that I'm fighting against. L polynomial identities I'm fighting.
This list that you are getting from as a consequence of Ras-Safra on step 3, you are
Yeah.
only taking the list for Q naught, or are you also going to take the list for?
No, I'm only taking the list for Q naught.
That's the part. So you're taking the list for.
So once again, let's see how the list is got. You take the Q bar. Q bar is itself m plus 1 polynomials. Let's just focus on the first coordinate, which is our f. Ras-Safra tells you, of course, we're going to do Ras-Safra on all the Q m plus 1 cases, but Ras-Safra tells you the first coordinate itself, you commit to list of n polynomials. So that the behavior, if ever the test passes, it has to be what one of these L polynomials looks like. So let's look at those L polynomials. It might be that these some of these L polynomials are 0 at h bar m, some of them are not. Whichever them are not 0, discard them away. Prune this list to keep only those which are 0 on the h power m.
You have the polynomials, you can actually.
See them. Now you know which one of them. Keep that list. And for those polynomials, extend them suitably to get the Q1 to QL. Further this one. And now I want to say, run this whole operation.
Yes, so Ras-Safra tells you that conditioned on the fact that the test succeeds, with probability 1 minus delta, it is explained by one of the keywords.
Yeah.
But what if all that 1 minus delta mass lies outside H power?
Sorry, can you repeat?
So you are saying conditioned on the fact that the point plane test succeeds, with probability 1 minus delta, it is explained by one of the keywords.
Yes.
But what happens if all that 1 minus delta mass lies outside H power n? Then how do you say one of the keywords must vanish?
No. So it doesn't say condition. It says this. It says the probability that the test passes and it is not explained is very small. Therefore, now we have gone into a region where the test has passed, and it is being explained by one of the polynomials.
Okay.
Now, once it's explained by one of the polynomials, suppose these polynomials were not, so it could have been it was explained by the polynomials which are actually further pruned away, the ones which are not passing the 0 and sub Q. How many of them are there? There are at most L of them. For each one of them, you have the Schwarzschild error, and that's all you will account for. So this list decoding version of writing it really captures this whole Fine. So it just extends this way. So there is a union bound, but now the union bound is very nicely kept. It just gets multiplied by this L this way, and that's the new error of the object. We'll have to, if I write it formally, it's going to take longer, but this is what it is, and this is just, and the L plays a role over there. So I can't have L to be too large. Okay, and that's basically actually, so it lends itself very, very cleanly. If you look at it, it's extremely clean how it lends itself to constructing the PCB. That's how you construct the zero on subgroup. And a similar sort of process goes into constructing the arithmetization that I will skip. That requires more effort to be careful. You will incur some more Schwarzschild errors. This will add to some more things, but it's exact same thing you will have. You will eventually you will get a statement of this form. So you will get. So you basically, so this is, you can do similar process. And do the same thing. Arithmetization. Basically what we will show. So here we won't, a plane won't be sufficient. We'll have to pick a slightly larger object. Here a cube will come into the picture. We'll show that basically this is what we will show. It is given a 3-sat formula P. And a proof Q bar, which will now I think it will be f power m to, it won't be f, that will be some order m. There will be more number of coordinates because I'll have to encode both the formula as well as the assignment. I'll have to do both of them, and you have the probability. This will be omega. Omega will be like a 3-dimensional object. And there will be some underlying test. Q bar is this a? Basically, the statement will be of the following. This one, there will be this, like that. We'll give this, and we'll give a test. And we'll give a test, some test, say predicate pi, which queries a 3-dimensional object, not a 2-dimensional object, a 3-dimensional object omega in f to the m, runs a bunch of tests, a low degree test, this sort of Schwarzschild test, and all of them. It will have the following feature, such that for all Q bar from f to the m to f to the order m, so all potential proofs, there exists Q1, Q2, Qn, and for all delta, which these are honest proofs. These will all be honest proofs. So in particular, if the formula is unsatisfiable, there will be no such Q1 to Ql. So that the probability, I pick omega, Q bar restricted to omega passes test pi, and there does not exist a I such that Q bar restricted to omega is not equivalent to Q bar restricted to omega is less than or equal to delta. The same sort of thing.
Same kind of thing.
It's the same kind of stability. This is stronger than what we wanted. Because all I wanted to prove was if the formula was unsatisfiable, then the probability of passing is delta. Notice that's going to happen exactly because when the formula is unsatisfiable, there is no Q1, Q2, QL. Therefore, such a thing can never happen. Therefore, you only have this statement and that's less than delta. But we are also going to give something when the formula passes. You're saying even when the formula passes, whenever it is passing, it's passing because of some agreement with some global proof. And that's, you should be able to see why this happens from this one. It requires a bit of work, but it is not hard to believe given what we did previously. Okay. And what I want to say right now is we actually have a robust PCP at the end of this. It's a so I have got it. What's the this is what's this PCP? This PCP is let's stare at it. So let's assume we have got this statement. Any questions on this? And then we will reinterpret this as a label cover problem over a large alphabet with subconstants on. Notice I have got this for every whichever delta of my choice. And the key point to notice is this delta is under my control. Delta was what came from the Schwarzschild error and the low degree test error. So these can be made really, really small. They can be made subconstant at this point.
Then what goes up if they make delta small?
Huh?
The degree goes up.
So the T over F is going to make so making delta small. The delta can't be made smaller than M over polynomial in D over F. So as long as D over F, you keep it this one. The field size to D will be the field will be a very large fraction compared to the degree D. But it can be like 1000 times D. You can keep it. You can make it as small as you want it. I haven't proved this, but this is also once again a whole lecture. This lecture, this part of it is tried by Srikanth, and actually nowhere, no paper this was written. Srikanth does every detail of it with excruciating care in his note, in the scribed note. So should go up and look up this. He does this to all details in the 2010 version of these notes. Okay. What I want to say now is right now we actually can view this as a label cover problem. In what sense? So look at, and so there are two ways to view this. This is, I want to say it's both a label cover and a PCP. In the PCP sense, what am I stating? I'm stating that you give me this, the proof is this object of size f power m, in which at every location you are giving me this huge alphabet of f to the order n. The alphabet is really, really large. The alphabet is humongous at each place. But then you're stating that the probability that this test passes, in fact, not just the probability that the test passes, you're stating that the expected, it's like the line point test. The line point test is better than the, notice it's an expected robustness. It's not the soundness of it is expected robustness. It's the expected robustness of this test passing is very good. So in other words, if I convert this into a label cover problem, where, so if I convert this to a label cover problem, on one side, I give f power m, and this function over here is basically this q bar to f power m to f power order m. That's what this function gives me. The other side, I have all possible objects that I'm going to query. That is, let's think of our 0 and subcube. I have every plane. And what I give over here is an accepting view when restricted to that object. And I'm obviously going to connect that object. That's this one. That's exactly the test which I'm stating there. I'm going to pick a random omega and I'm going to query all points in omega. So this is this test. That's exactly the label cover 2, the 2 query PCP to robust PCP reduction. And what we have shown is this label cover problem actually has very low soundness error. We have shown that the gap 1 delta for this label cover problem is the delta.
Recording in progress.
This delta is the same delta as that. That's exactly, this is, if you believe the previous statement, this is exactly what we have. And notice we have got delta to be arbitrarily small as we want. This is what we want, sort for. So are we done? We wanted a label cover, and this was previously we had got this with parallel repetition. Now the question is, we have bypassed parallel repetition completely. We have got something. We have got some constant delta just from low degree test. Just from much better analysis of the low degree test, we managed to get it. We didn't need the power of parallel repetition to do this. We managed to get this. Question is already done. Slight caveat to it. Let's look at this is.
So you want to look at the size of sigma.
Yeah, are we done? Question which you want to ask is. Are we done? So, no. Large alphabet size. Actually, the alphabet size is large from both ends. F to the order m itself is large. F to the order m is log m. M is itself is log m. This is log m to the order log m, which is super polynomial. The alphabet given at every step is super polynomial. This is not good enough for any hardness reduction, because if you're going to do this with long code, you're going to take a 2 power the alphabet size. That's just going to kill the whole reduction. We got label cover, if you all we want, everything is nice.
Very long, but as long as the alphabet size is order logging, it's
Alphabet is.
as long as the alphabet space is order logging.
The alphabet size should be order log n. Here the alphabet size is poly log m, or like actually more than, in fact it's polynomial in n. It's polynomial in n here. It's actually terrible over here. The point is we have got something too good to be. We have got very good soundness, but we are paying at a huge cost. We are paying at a cost of the alphabet size. Notice that in some sense, there's not something to be here. If you expect that, if you allow the alphabet to go as large as n, then you can get soundness 0. You can say the whole proof is one symbol. You read that symbol and obviously the soundness is 0. I'm saying, okay, I'm not going to give one symbol, I'm going to give slightly smaller than one symbol. So I'm not going to give poly n, I'm going to give n square root n alphabet size, and I'm getting a good. So if you allow the alphabet size of poly n, order n, then getting soundness to be 0 is trivial. You put the whole proof in one symbol alphabet, obviously you can make it this one. Here I'm saying, okay, I'm not going as bad as that. I'm making the alphabet to be like poly in n or something like sub-polynomial, and I'm getting this one. But can I got something over here? Can we do something better than this? Okay, this is the problem over here. So we will now tackle this using composition. We'll do alphabet reduction to get around this. Is this problem clear? If this problem is clear, then we'll see how to. So let's just stop for a few minutes, understand if we follow what the issue is.
This is when you do on this in approximability results, we prove this up to hypercube of size 2 power sigma. And
Yeah.
becomes steady.
Yeah, then you can't afford that. So for all of that, sigma has to be logarithmic. If you,
Hypothetically speaking, if there was some PCB not based on the long code.
then you can. So there is work on that also. That's why it's called, there are works called the short code, which are substitutions for the long code. This one, but they also, it's not that they get polynomial size work, they just get sub exponential. Well, the long code is really nice. So there's work on all of these directions, and we are nowhere near an optimal TCP. Okay. So now I will resort to. This. Yeah. So basically, this is a problem which Moshkowitz and Raz solved. The paper, what we will now analyze is the paper solved by Moshkowitz and Raz, but the solution I present is a solution due to Elite and myself. So basically, this is where we are. So I'm going to just give back in the context. We have the gap level cover, one minus this one hard, and this is shows up to some constant. Now, we would like to get subconstant delta, and paralleliptition gets you this. And if you want to go to subconstant delta, the claim is what does Raz, Safran, Arora, so then give you? They give you this. Except that the large alphabet size renders it useless for hardness reductions. This is where we are at this point. So we want to take this and we want to further reduce this. We want to take this and improve this. This is exactly where we are at this point. We want to get rid of, right now this feature is true only up to n polylog n. I want to get this sigma all the way down to constant. That is, it might be true for such large alphabet sizes, but I also want it to be true for smaller alphabet sizes. And this is basically the main result of Moshkowitz-Raz. They remove that lower bound. They say how you can take the upper bound and then get it down all the, prove no lower bound on the alphabet size, get it down for everything. That's what Moshkowitz-Raz gets. And what we will see is basically.
So they also get a nearly linear time.
Huh?
They get the reductions are super.
The reduction will be far, far better than parallelization. But that's just got by the fact that you think, for example, everything that we done is really nearly linear right now. Why is it nearly linear if it's cubic? Huh? You could assume that the two directions were coming from a subspace. So getting nearly linear is, you don't pay any extra work to doing this.
So this alphabet reduction uses the fact that this is coming from a relativity or it's for a general level.
We will show it for a general level. All of this is fine. And this is just the usual reduction. So why is there a way to go in the presentation mode? This is just to say PCPs and label covers are the same if you work with robust soundness. Yeah, that's just the fact that two query PCPs and robust PCPs. Same if you, now you're not talking about probability of disagreement failing, but the expected agreement, expected probability, the agreement will satisfying the local view. So what does this tell you? That if you want to get label cover, this one, hardness, you need to get, you want to label cover this one, you need to construct robust PCPs. PCPs in which you have robust soundness of error. What is robust soundness of error? In the yes case, you should pass with probability 1. In the no case, not just your probability of failure should be low, the expected agreement of the local view satisfying and accepting local view being expected distance of the local view to an accepting local view should be small.
Large.
This expected distance is the robust soundness error. We want to keep this. This is what we call robust soundness. So we want to construct a PCP for which robust soundness is small. Notice original PCP composition which we did not preserve. Did it preserve robust soundness? One second. Let's. I want to talk about a composition. Okay, so I need to reduce the number of queries once again. So we had to reduce alphabet size, but I'm going to I had reduced alphabet size in the gap label cover world. In the robust PCP world, these are two different viewpoints of the same problem. They are syntactically the same problem. In the gap label cover, I had to reduce the alphabet size. When I view it in the language of robust PCPs, this is reducing the query complexity, because the alphabet size comes from the query complexity of the robust PCP. I need to reduce the query complexity of the robust PCP, maintaining robustness. If I reduce the query complexity of the robust PCP, maintaining robustness, the new robust PCP will correspond to a gap label cover which has low soundness error. Okay, so that's going to be our goal. Given a robust PCP, I want to reduce the error. I want to reduce its query complexity. Composition was a task which was precisely designed for this purpose. It was designed to do it. So let's just recall what composition is. This is PPTs. Forget about all of this. And composition, Aurora Safra in the early 90s designed composition exactly for this, to reduce query complexity. They said you read a particular window, you want to accept this. Now instead of reading that window, you invoke another inner prover to check that. That's what we had done, if you recall. And we had run into all of these issues in the past. So composition, how it was done. That then the inner verifier need to not only check that F is satisfied, but also satisfied. That's why we defined the notion of PCPs of proximity. The AS and ASLMS did it by hard coding things. This later on, BGHS, we had come up with this notion of PCPs of proximity, which is what we saw, and that was how we defined composition. But there's an issue with this. It does not work. Notice the very nature of the way for PCPs of proximity was defined was, we had said that this, we are going to PCP of proximity says, we're going to tie it down to this particular proof. Now there is no one proof, as we saw at this place, there are potentially fewer proofs. So how are you going to tie it down to any one proof? So this solution does not work for us, because at such small soundness error, the notion of PCPs of proximity sort of breaks down, because you are tying down to the acceptance to a particular way the proof works. There is no particular way the proof works. There could be L possible ways the way the proof works, and you need to be fighting against all of them simultaneously. So what we will do is we'll define another object an inner object which will not be the PCPs of
So
proximity.
would you repeat specific models of this?
So what do PCPs of proximity? Why did we even define PCPs of proximity?
So we had a look, we cannot read the whole input, so we say that the circuit is the global input
Mhm.
and the assignment to the circuit is part of the local input.
Yeah.
So we can locally read the local input and the proof, but we can globally read the circuit and
Yeah.
then we can check if it's satisfied.
Yeah. So, but then that was set, it was set up such that this particular PCP of proximity worked according to one global input. It was, now the point is, we know that the global outer proof could be cheating according to L different proofs. How are we going to ensure that the inner PCP of proximity can be working according to one particular global proof? It's going to say it's close to this particular outer proof. But potentially there are n possible outer proofs you are going to work against. How is this object going to be even working against n possible outer proofs?
So get it, yes, so suppose there are two possible values of the randomness.
Yeah.
And for one fixing of the randomness, the PCP of proximity is consistent with outer proof one. And for second one, it is consistent with outer proof two.
Yes.
They will say if they are consistent with the same outer proof.
Yeah. So the question is, how do you notice which is the PCP of proximity you are going to work with? It's unclear. So what you want to do is want to come up with a definition that by itself will allow the inner PCP of proximity to work with to be consistent with multiple proofs. The way right now the previous definition did not allow the PCP of proximity to be consistent with one proof. It could only be consistent with more than one proof. It could only be consistent with a single proof, and it could be decoding because it was essentially decoding. It was
Locally decoding each coordinate.
locally it was essentially decoding a coordinate according to a particular proof. Now I want to say that it could possibly decoding according to multiple proofs, and I need to make this into the definition. So it's going to be a very minor change in the definition. So we will define the definition. We're going to change it so that it actually the same. So PCP. The PCP of proximity was basically PCPs were local encodings of the NP witness. But they were even more, they were encodings of NP witnesses which could be locally decoded. And this was what we were using in the PCP of proximity. We were locally decoding it from the inner proof, checking it against the outer proof, and checking that these two values match against each other. So let's make that process explicit. So I'm going to write this. So I'm going to ask. So previously, I quit. So I want now the decodable PCP to output previously the PCP of proximity I only ran tests on it. I didn't decode values from it. Now I'm going to ask, why did we use the PCP of proximity? We wanted to compare some bit in the outer proof with some bit in the inner proof, and that's what we did. So we could have instead said the inner proof lets me decode this value, which I will then check it against the outer proof. So now let's exactly do the decoding ask. I'm going to say it's going to decode certain values. So the outer proof is querying Windows I1 to IQ, and I want to, if FP1 equals YI, I agree. If FPI is not this one, I'm going to reject. This is sort of the decoding object I'm going to give. And once I write it in the decoding value this way, I can now say that actually it decodes not according to one particular outer proof, but possibly according to L proofs. And if the decoded value is not consistent with any one of the L proofs, then I reject. This is exactly like the statements which we have seen so far. So I will, instead of writing a PCP of proximity, I'll expect the inner object to be a decodable PCP, which says that I'm going to ask it to return values of the outer object. I'm going to ask it to return. And I'll say, given any inner PCP, I can commit it to one of L possible guys, so that whenever it returns, either it fails or whatever it returns is consistent to one of L possibilities. This is a thing that's feasible given what we have seen so far. So let's define this object. This is what I'll call a decodable PCP. So it's used like the usual PCP verifier. One second, let's see if we follow this definition and then we will. So basically it wants to decode a particular index of the NP witness. So now previously PCP of proximity, how was the PCP of proximity? You just want to check something in the NP witness was true. You checked the certain part of the PCP of proximity where you are querying into the NP witness. Now what I'm going to say is, I'm going to ask the prover to decode that particular value instead of one. So I'm going to tell it, decode to me the NP witness corresponding to location I. So it's going to compute some window I want to IQ, go into that window in the proof, read that. Now, if there is an NP witness that actually satisfies the original threshold, then there is another proof that satisfies this, so that not only the predicate passes, but also it will, when it's fed I, it will output the ith value of that particular NP witness. Now, I want to say for any other pi, there is a list of at most y1 to yl satisfying witnesses to the NP predicate, such that the probability that this does not reject, but yet returns consistent with one of this is very, very low. This is exactly the same sort of statements we have seen. So you can expect that statement we got from the PCPs that we have constructed from the low degree test. So what I want to claim is all the low degree test based PCPs that we have seen so far till the end of till about 15 minutes ago would actually construct to you such a decodable piece. Is the definition of this object clear? It's exactly a PCP, except along with the PCP does not expect you to return a particular value yi. It's going to say reject or accept. Here I'm saying I want to, in addition to it, I want you to return to me the ith bit of the original NP witness. And this was exactly what the PCP of proximity was also doing. You were getting this, you were going to get this value and check it against what was there. Here I'm saying decode it and give it to me explicitly. And the reason this definition is a bit nicer, it's stating that for in the right case, there is one proof that it always decodes correctly. For every other proof, this is not just in the sum, not just when phi is not satisfiable, even when phi is satisfiable, for every proof, that proof can be tied to a list of honest to God NP witnesses, such that whenever the predicate returns a value which is not reject, that value is actually consistent with one of this with probability, with very high probability, but for probability delta, it's consistent with this. And notice this is not a statement just for phi which are unsatisfiable. This is a statement for all phi. Okay.
For satisfiable P, you just take one.
Satisfiable P, there is one which satisfies this. But even for satisfiable P, I want to say whenever a pi passes, it's passing because because it's consistent with L things are explaining it. I want to say, though I have defined it and all, this is not really a new object. It always existed in. So now let's see, given this DPCP, let's see how we can compose it to get our. What was our goal? We wanted to construct. We had a robust PCP which had very good soundness, but a large query complexity. We wanted to now construct it a robust PCP with still reasonable soundness, but smaller query complexity. Composition was exactly designed to do this. Previously, we did composition with PCPs of proximity. Unfortunately, they didn't work in the this error regime. That's why we are going to work with DPCPs. So let's work with DPCPs. So as you input, the outer guy, he computes his window I and the predicate he wants to compute on the window. Now, instead of checking that F restricted to pi I is 1, it's going to invoke a decoding verifier to do this. That's what this is. So in addition, now to ensure that the different decoding verifier is 1, it's going to, in addition, select a random location in I and ask the decoding verifier to output this symbol. And it will check consistency against this. So essentially the figure is going to look like this. This is the outer proof, pi. The outer verifier is going to query some location I in it and make some predicate F. This is too large a query complexity. It can't enter this. So what it's going to do, it's going to instead invoke another pi IF. Notice there will be such a pi IF for every I. For every choice of randomness, there will be this. It's going to incur this. But how does it know that this guy is consistent with this? It's going to say this is checking that this guy is satisfying some predicate. So that's the predicate for this object. So it's going to say this is the NP witness for this. It's going to say return to me an ith, decode to me the ith value of this. So it's going to read this smaller thing over here. And that's the ith value. It's going to now read this one location along here and make this check across. It incurs an extra query. So the query is unlike the previously we just had this one because the PCP of proximity involved this and this previously. The way we had the PCP of proximity was it involved both these parts. Here we are separating decodable PCP is this. It decodes and decodes to this value. Now the query complexity is this plus this. Is the composition clear? Okay, it incurs an extra query. I don't care about it. It's this one. The nice thing about it is it works for low soundness composition, and this is how actually low soundness was done in Aurora, Safra, RAS, Southern, Aurora, Southern, RAS, Safra, DFKRS, all of these. Actually, this is exactly what they did. Because an extra query.
That is fine.
That's fine. The question will be, does it preserve robustness? Eventually, if you want gap label cover, we want it to be robust piece. What does it mean to be robust? The expected distance to your satisfying view should be small.
No, if you are getting label cover itself for robustness, you are not composing.
No. We are not yet got it. If a robust PCP is to be viewed as a label cover, then it should be robust sound. If a PCP, notice a PCP is not a label cover by default.
Okay.
For a PCP to get a label cover, you are viewing a PCP which is a large query object as a two query object. For that to happen, the PCP should have robust soundness. The question is now, is this composition sound robustly also? It's sound, but is it robustly sound is the question. That is the expected distance of what is the new verifier's local view? It is this part and this dark part. Is this guy, what is its expected distance from an accepting local view? Notice it's already an involved question. The proof, the local view has two parts to it, one from this and one from this. I don't know how to put distance on both of them. I don't know how to split the distance. Let's, for the best of worlds, assume that the outer guy is robust, the inner guy is robust. As good as it gets. Question is the composed guy robust? If the composed guy is robust, then by the correspondence we'll get this. Unfortunately, it's not robust. For similar reason, these are two different objects. I can always make one of them satisfy the view, be perfect. That is, all the discrepancy can happen only in the consistency test. Therefore, So it can always be satisfied, it can always be half closed to an accepting view, whichever way you put the distance metric on it. Therefore, the view consists of two parts, each can be completed to an accepting view. And so this can never be made into a robust PCP which has soundness smaller than half.
We can add more consistency.
Whatever done, the proof is of two parts. And as long as the proof is of tautologically two parts, each part can be consistent, each part can be consistent of.
If the number of consistency tests is more than the number of the.
So what we are going to do is we'll do a simpler task than that. Why did this issue happen? Because there were two parts to the proof, the outer proof and the inner proof. Why did we need two parts? Because we had to check consistency across them. Why did we need to check? We needed to check that there are several inner parts which are all decoding to the same outer object. We needed to check that they were consistent with each other. And this is why we had the outer object. Let's get rid of the outer object completely. Let's take all the inner objects, just compare them against each other. So what I'm going to claim, instead of decoding from inner proof and comparing to pi I, let's compare the inner proofs to each other. So more precisely, so let's take the outer proof. The outer proof now only exists in the mind of the verifier. The outer proof no longer is going to be there. The only proof of this object is going to be all inner proofs. So it's going to pick up a random location in the outer proof. And it's going to look at several windows in which the outer proof is going to participate. So I1, F1 is one such window. I2, F2 is another such window. I3, F3 is another window. Each of these were things which the outer guy which we had done. We looked at all of these guys. We look at all such pairs, I1, F1, ID, FD. We run all the inner verifiers in parallel now. We run all of these objects, ask them all to decode them, and then just compare their values against each other. If they all are matched with each other, we accept, otherwise we reject.
Is there a reason to consider all windows and not many windows?
Yeah, so the proof actually goes that if all is too much, we'll use a sampler and pick up this one and that will work. So that's what we do. You could just consider all. Yeah. So the point was previously we were just considering two of them, that gave you half. If you consider three, so the bottleneck will be 1/3. So if you want to get soundness error less than epsilon, you have to consider at least 1/epsilon of these guys. So that's going to be the new composition. The new composition is basically, it's going to be a different take on this one. We build an outer object, a decodable PCP, and the way we do composition is this way. We take an outer thing, we look at all the windows it participates in, run all the inner objects that are run several predicates that, sorry, let's go with this one. Let's exactly what I did. Select a random symbol in the outer object. Consider all windows that contain it. We can do what Mrinal says also, pick up all windows and then pick a good sampler from it. But now let's pick up all windows. Then let's go to each of the inner guys and ask them to do the inner work. Then decode. And accept if all the inner verifiers accept and they all decode to the same outer object. So you remove the outer guy. So this whole reason for this robustness breaking down was because the proof was logically split into two parts. We just threw out the outer proof. We have only the inner proofs now. And then we compare. And why did we have outer proof? Only to measure consistency of the inner proof against each other. So we measure it against each other explicitly. To do this, and this works.
So you completely drop the outer.
We completely drop the outer. So replace the one consistency query which we had with decoding many local views simultaneously.
I was thinking of
Adding more consistency.
Yeah.
So that you overdo.
It's a clever.
Yeah, this is basically the paper that they read. That's the paper that they read, so, and that basically gives us, so you take an outer, this one, you run this, you get. The thing, it involves work to show that this maintains robust soundness. It's actually not it was 2 pages of argument. Can be done, it's not hard, just decoding everything comes into the picture. And then this is there in the notes, this is the 3rd lecture series, and this is written, this is there both in the paper with me and Edith, as well as in Ramprasad notes for the course. And that's basically the whole. And then we'll get. We'll basically get the Moshko-Uthra statement. Yeah, so basically the DH composition was defining this notion of decodable TCP, viewing it this way, and realizing that basically all that we needed to do was check them against each other rather than against the outer object. That did the job. Yeah. Unfortunately, this still doesn't give us the right relationship between 1 and sigma. These are questions which are still open, and would like to do this. I'm well within time, and I promise finished everything I wanted to do. Let's start with this.
We'll start 2 to 2.
We'll start 2 to 2 next time. Good.